So actually, I wanted to say, I don't know how many of you know, but Nick and I met even before our Berkeley times. We intersected at ETH in Zurich about, wow, that's 6 years ago. That was October 2014 or thereabouts.
Sure, turning off the coffee machine.
And actually, we started collaborating back then, and I want to say, like, Nick has done really a fantastic trajectory since then. And in fact, all of the wonderful work you'll hear about today has roots as early as Nick's master's thesis at ETH, which turned out to be a very, I think, lucky direction to go into. Because as you will hear today, Nick is responsible for the most efficient post-quantum zero-knowledge proofs known to date. So thank you all for attending, and I'll hand it off to you, Nick.
Great. Thank you, Ali. Thank you for also giving away the punchline of my talk. But I guess you could probably tell it from the title. So I'm just going to make sure that everyone is muted. Perfect. So thank you, everybody, for attending my talk. Please feel free to unmute yourselves and interrupt me if anything doesn't make sense, or if you have like a humorous quip that you want to share with everyone. Yeah, and I guess thank you for taking the time out of your busy VE day to enjoy this talk. So I'm going to be talking about proof systems, and I'm going to kind of start you off with a little story. So this is a genuine post from the MIT Confessions webpage. So this MIT student has a crush on another MIT student, but obviously they can't, reveal this publicly without making things weird. So to avoid making things weird, what they do is they publish a cryptographic hash of their username space their crush's username, and they post it on the MIT Confessions webpage. Right, so this sort of hides their identities. The problem is that there aren't really that many usernames at MIT, and so there's actually quite a weak crypto system, and it's very quickly brute forced by Charlie. So the names have been redacted to protect the guilty. So Charlie brute forces through all the pairs of usernames that there are, and he figures out who the original poster is and who their crush is. And sadly, the crush is taken already. Of course, there are some people who think that Charlie is just messing about, so he wants to convince these people that he has actually done this work and like found the two usernames that hash to this string, but obviously he doesn't want to like post the identities of these users on the MIT Confessions website. So he asks, can any cryptography nerds chime in? And chime in they do. So a helpful cryptography nerd comes by and says, I believe you're looking for a ZK snark. So he was correct. And let's sort of see why that is. So what is a ZK snark? A ZK snark is a zero-knowledge, succinct, non-interactive argument of knowledge. So, big acronym, but we'll break it down. So you start always with some statement that you want to prove. In this case, it's a statement of knowledge. It says, I figured out who you are and who your crush is. So let's convert it into some sort of mathematical statement that we can actually prove. So this is, I know like username A and username B, like Alice Bob, such that the hash of A and B is equal to Z, which is this public value. The way that you prove this, the way that we sort of model this is you have a prover who is Charlie, who produces a proof that he then sends to the verifier, who could be anybody. And in order for this to be useful, you need to have certain kind of natural properties. And the first one is completeness. So of course, if the statement is true, you should be able to prove that it's true efficiently. So sort of polynomial time. The next property you need is a sort of soundness, a computational soundness. So this says that if the statement is false, then it should be hard to produce a proof that is convincing. This is a little bit different to the sort of statistical soundness. Statistical soundness says there really does not exist a proof that's convincing. Here we only want a computational property. So it should be hard for someone who is computationally bounded to produce a convincing proof. And the final property we need is some kind of succinctness. So like the proof should be sort of short. So in this case, short, I sort of mean some fixed polynomial and the security parameter. It's not super important what that is. You should just think about them as being short. Okay, so far we haven't really done very much, because you could more or less, like a proof that satisfies these properties, and actually stronger properties, is just providing A and B, right? That hash to Z. And so obviously this doesn't like fulfill the guarantee that we kind of didn't reveal who the users were. And so we also want this property of zero knowledge. And basically zero knowledge says that the proof pi only tells you that the statement S is true and nothing about the so-called witness. So these A and B that make the statement true. Orthogonal to this, there is also another property that is maybe less useful in this situation, but is still very important in practical applications, which is what's called sublinear verification, or scalability. So this basically says that somehow I should be saving work by doing this proof. So the prover can provide me with a proof, and the time for me to verify that is less than the time that it would take for me to check the statement myself. So we'll see a bit more later about kind of why how that can be useful. Are there any questions or any technical problems that I'm not seeing?
It seems that in this example, T of S is short, so maybe.
Yeah, so in this example, T of S is pretty small, and so you don't have to worry about it. You could imagine artificially making this more difficult by having for example, replace the hash function with a hash function iterated on itself like 1,000,000 times, right? And then maybe you don't want to run this computation once through to verify. But yes, in this situation, the hash function anyway is efficient to compute, so it doesn't. It's not really a factor. Okay. So what are some applications of these things? So broadly, the applications focus on sort of one of the two aspects of privacy, so zero knowledge, or scalability, which is the succinct verification, sublinear verification. There are lots of applications where kind of having both is nice, but usually there's one that's more important. So in terms of privacy applications, essentially anywhere where you use a zero knowledge proof, you can use zk-SNARK, and often you will get something which is sort of more efficient, basically because of the kind of good efficiency properties of SNARKs. So for example, you can use them to build group and ring signatures. You can use them to bootstrap semi-honest into malicious secure multi-party computation. You can use them to build CCH secure encryption from CPA secure encryption, and so on. Also identification protocols. The kind of classic scalability application is computational outsourcing. So like you have some computation you want to run on your machine. It is too costly to run on your machine, and so you ask someone else to do it. But then you want them to prove to you that they did the computation correctly, and you need this to cost a lot less than doing the computation by yourself. So this is kind of the natural kind of scalability application. I just want to mention sort of two exciting new applications that come from sort of decentralized systems and cryptocurrencies. So the first one is sort of blockchain privacy type things, so like transaction privacy for cryptocurrencies. Obviously, the zero knowledge proofs are a very good way of achieving simultaneously transaction privacy and integrity on the blockchain. And on the scalability side, there are actually some very interesting works, like very interesting progress in using these types of proofs to help scale decentralized computation. So there are problems in current cryptocurrencies that basically the throughput of the network is very slow because everybody has to sort of recompute everything. So the ZK snarks can be used to kind of avoid this bottleneck, and there have been there's been a lot of interesting work, and one in particular, the Starkware, this company, ran some experiments showing that if you use ZK snarks in Ethereum, then you can go from 15 transactions per second to about 9,000 transactions per second throughput in their experiments. So this is some very exciting applications to decentralized computation. Okay, so why am I talking about this? So a good chunk of my work is about snarks. As you can see from this picture, about 2/3 of it. I've also done some work in more sort of standard complexity theory. And similarly to the two bubbles of snark applications, these works tend to focus on either scalability or privacy, sometimes both, but mostly one or the other. And in addition to these kind of two categories, there is also this red box, which is post-quantum security. So this is kind of one of the central themes of this talk, which sort of touches upon all of the different aspects of my work. So it kind of summarizes really a lot of the things that I've been working on. So I guess a couple of things that I won't get to talk about today in the post-quantum security bubble. Firstly, this work with some people from IBM and Max Ovsyankin, who's at Berkeley, on snarks for lattice problems. So this is basically you want to build some post-quantum crypto system from lattice assumptions, and you need like a zero knowledge proof about some lattice primitive. How can you build such things? And this other work, which is sort of it was also kind of about post-quantum security, but in quite a different setting. So this is about doing zero knowledge in the MIP star model. So it was building zero knowledge protocols in the MIP star model. And you might recall that the MIP star model is where you have two provers that are spatially separated, but they share quantum entanglement. So this is sort of just a summary of everything that I've done in the area. So now let's sort of go back to like 2015, when I started my PhD, and when we knew quite a bit less about snarks than we do now. So the first thing that we really knew about snarks was that they're impossible. So there is a black box impossibility result, really beautiful impossibility result from Gentry and Wicks in 2011 that basically says that you can't build snarks black box from standard assumptions. So that is very unfortunate. But seeing as snarks have such nice properties, it's worth trying to understand the assumptions from which you can build them, even if they're non-standard.
Sorry, Nick, what is a standard assumption?
So by standard in this context, I mean explicitly, I mean falsifiable. So this means that there is basically some way to prove that I've broken the assumption in polynomial time. So like basically all of the standard cryptographic assumptions, things like one-way functions and discrete logarithm and things like this, these are falsifiable assumptions. Okay, so we can make some more exotic assumptions, and it turns out that this is very helpful in building snarks. So you can actually sort of circumvent this result by making a more exotic assumption. So there are many constructions from various different sort of non-falsifiable assumptions, or in other models. And on top of this, sort of more recently, there have actually been kind of real implementations in the real world that they take some of these constructions and they implement them in code, and they're like not, they're actually things that you can run and use on in a real deployed system. This is advanced to the point that you can now actually build cryptocurrencies that have these technologies inside of them that hold value. So that's pretty exciting. So this all looks like really very rosy, right? I mean, besides this, having to make these non-standard assumptions, which is something that we still don't know how to get around. Basically, smart constructions are amazing, and there's a whole variety of them. And they're even sort of practically useful. So like, what is the problem? Why am I sitting here today? And the answer is quantum computers. So quantum computers are, progressing at a reasonably rapid rate. Actually simultaneously to my talk, I think there is someone at Google is talking about these programmable superconducting processes and quantum supremacy. So I probably shouldn't have said that because I guess everyone might leave. So there was this breakthrough at Google where they sort of achieved some kind of quantum supremacy. They had a quantum computer perform a task that it is not believed that classical computers can do efficiently. So maybe you don't trust Google, in which case maybe you trust NIST. So, NIST is very concerned about the threat of quantum computers to cryptography. And so they're very interested in kind of standardizing post-quantum cryptography and developing this new type of crypto so that we're ready for when post-quantum computers when quantum computers arrive. If you don't trust them, perhaps you trust the military. So there is actually a DARPA project explicitly about post-quantum zero-knowledge proofs. So they are very concerned about ensuring that zero-knowledge proofs remain viable even if cryptography-relevant quantum computers become a reality. And if you don't trust any of these organizations, maybe you trust Netflix. So this is a still from the show Altered Carbon, which is set in the year 2414. Yeah. In the show, there's a character who's like gone to a shop and is trying to buy something. And if you look very closely, you can see that what they're trying to buy is priced in Zcash. And so you would hope that if we're still using Zcash in the year 2414, it should be based on something which is post-quantum secure. All right. So what happens if we kind of add post-quantum to this, like we kind of require post-quantum security? And the answer is that the picture looks much more bleak. So essentially, all of these constructions are susceptible to quantum attacks via some variant of Shor's algorithm. Like they all rely on basically the hardness of the discrete logarithm problem at the very least. This means that in the quantum setting, we have very few constructions that work. In fact, only one construction that works as of 2015. And moreover, all of these implementations, all of these, the stuff that's used in cryptocurrencies is broken. Okay. So there is one thing that's left.
Can I ask a quick question?
Oh yeah, go ahead.
So being broken means like soundness or the zero knowledge? I guess soundness, yeah.
Yeah, so it is soundness in all of these cases. Yes, so the zero knowledge is usually statistical.
Got it.
Yeah. Yeah. Okay, so let's talk about this one construction that we kind of have left. It's actually the sort of original construction of SNARKs due to Sylvia Macaulay in the random oracle model. So how does Macaulay build this plausibly post-quantum SNARK? So what he does is basically there is some efficiency preserving transformation from a model called a probabilistically checkable proof, or PCP. So this is a model where you have a long proof string that the prover writes down, and then he goes away, and the verifier can come along and he can like choose a few places in the proof to query sort of at random, and then decide whether to accept or reject. And there is a seminal result about PCPs that essentially you can efficiently check statements using PCPs. In particular, so if you have a time t computation, you can prove that it was done correctly in time, which is polynomial in t, and verified in time and sort of number of queries that is polylogarithmic in t. And so what this gives you on the other side is that you have a prover that runs in polynomial time, an argument size which is polylogarithmic, and a verifier time which is also polylogarithmic. So like this is really very good, right? You kind of, this is a almost exponential improvement in the time to verify versus the time to prove. So that is great. The question then is like, why don't we just use this, right? Like what am I doing? And the answer is a sort of practical concern. So don't worry, there will be some more theory after this, but there are some practical concerns. So there are sort of two aspects to this concern, and one of them is a scalability problem, one of them is a privacy problem. So in the scalability setting, the kind of most important graph is this execution time versus computation size graph. And native execution looks like a straight line, right? As you increase the size of your computation, it takes longer to execute. Verification, on the other hand, looks like basically flat because it's polylog, right? But the overhead is significant, and so kind of it starts much higher up this y-axis. And the point at which these two lines cross is sort of the threshold for usefulness for this scheme, right? Like you wouldn't save anything if you tried to prove a computation that was on the left of this line because the verification is slower than the native execution. So the question is, where is this line? And the answer is that for the state-of-the-art PCPs, this line sits at about 1 trillion gates, something like that. And this is like way more than we are able to prove. I think it's like 1 million times larger than we're able to prove right now. Like this is just completely like, you know, this is like 100 years away or something, more than that maybe. So this means that essentially we can't use these systems right now. At least not for scalability purposes. So you might say, okay, what about privacy? Like for privacy, I don't really care about verification being faster than native execution. I just care about zero knowledge, right? And so let's kind of look further down the computation size graph at a sort of practical computation size of about 1 million gates. This corresponds to like 100 millisecond computation, something like that. If you want to prove such a thing, then it would take you essentially more than a day with a PCP. And this is even without adding zero knowledge. So you have to pay, like there is a cost to including zero knowledge, and the cost is, I mean, I can't compute it for you, but it is significant. So it would be maybe like 10 times worse. It might be like a week to prove this in zero knowledge. So again, this is really not very useful. Okay, so let's kind of summarize this this little section. So SNARKs are important, and there are many practical constructions of SNARKs of various shapes and sizes. Quantum computers are also important, and they are sort of rapidly improving, and so it makes sense to like think about post-quantum SNARKs. The problem is that firstly, we don't know any post-quantum snarks unless you kind of add this caveat that they're only plausibly post-quantum in the sense that like there's no attack, or there's no known attack. And once you add this caveat, there is a single construction, which is this classical construction due to Silvio Macaulay, but it doesn't lie in this intersection, right? It's not a practical construction for any of our applications. So, you know, this is unfortunate. This is something that we want to remedy. And so, how do we do this? Well, one thing we might ask is, okay, we like this Macaulay construction, like it has a lot of nice properties, but can we plug something into it that is better than PCPs? Obviously, this doesn't really make sense because the Macaulay construction is for PCPs, but this is a good starting point for our thinking. And the key idea here is that interaction can make proofs more efficient. So where does this come from? Basically, in this work that came out of my master's thesis, we defined this interactive generalization of PCPs. So this is with Elie Ben-Sasson and Alessandro. It's called an interactive oracle proof. And the way that it works is as follows. It starts out sort of looking just like a PCP. So you have some long proof string that the prover writes down, and then the verifier can query it. The difference is now the prover doesn't go away. So the verifier will send back some random challenge to which the prover can then respond with another PCP string. And this can continue for some number of rounds. And at the end, the verifier has all these PCP strings. He makes a bunch of queries to them and decides whether he's going to accept or reject. So this is a sort of more general model than PCPs. And this additional power allows us to prove things that we don't know how to do, or rather build constructions that we don't know how to achieve with just sort of these one-round PCPs. For example, with a 3-round IOP, you can get something where the proof length, as in the sum of all of the kind of big proofs that I send, is linear in the circuit size, and the query complexity is constant. And if you were to get this for PCPs, this would be like a major breakthrough. And sort of more on the practical side, we have 3-round IOPs for arithmetic circuit satisfiability, which have like a lot of nice asymptotic properties. So they have quasi-linear prover time, query complexity, which is logarithmic, and zero knowledge. And again, zero knowledge for PCPs is something that can be achieved, but you pay kind of an overhead for doing this, and in this setting, you don't. Okay.
Nick, I have a question. So by 3 rounds, do you mean that a verifier just sends a single challenge and the prover responds with another PCP?
No, I mean, by 3 rounds, I mean like 6 messages, basically.
Okay.
Yeah. Yes. Okay. So now, how do you build actual post-quantum ZK snarks? So remember that we're aiming for something that is non-interactive. But what we do is we start with something that is interactive, this IOP, and then we apply a transformation, which is sort of related to this Macaulay transformation, which preserves both efficiency and zero knowledge. And this converts this IOP into a non-interactive snark, so a short non-interactive proof. And moreover, we can show that this transformation actually yields a post-quantum secure snark. So this is secure in the quantum random oracle model. So this is, now this is no longer kind of plausibly, this is like proven secure in this quantum random oracle model. And the idea that kind of that pushes this is that if you allow interaction in the proof side of things, you can obtain non-interactive arguments on the cryptographic side that are sort of better. So let's kind of explore what I mean by better, like what that actually results in. So let's look at the example of proving a 100 millisecond computation. So if you used a SNARK built from a PCP, these are estimates because no one, this hasn't been implemented because it would be extremely bad. The prover time would roughly be days. The verified time, something like a second, maybe. The argument size is like 100 megabytes, on the order of 100 megabytes, and there is no zero knowledge. So basically, there is no situation in which you would want to do this at all. But if you take kind of the state-of-the-art IOP-based SNARK, then all of these parameters improve significantly. So the prover time is a much more reasonable 20 minutes, which may be fine for certain applications. The verified time is 10 milliseconds. The argument size is a respectable 250 kilobytes, and you obtain zero knowledge on top of all of this. So one thing to note is that this verified time is 10 times faster than re-executing. So we do actually obtain this like sublinear verification. And my contribution to this is basically developing tools that allow these efficient IOPs to be built. So these developing general tools that allow us to build all kinds of interesting constructions.
And
Okay.
Nick,
Yes.
I have a question about the model, the IOP model.
Sure.
So you're saying that you're sending, like the prover is sending oracles to the verifier. Should I think of these oracles as black box? And if so, what if these black boxes have like qubits that are entangled with one another or something? Like, is this captured in the model, or are these deterministic black boxes?
I see. So the model itself doesn't. So the model itself enforces that these strings are like bits. So there is no, like in the IOP model, there is no like entangled anything. It's like it's an information theoretic model. Nobody is computationally bounded, and the strings are classical bit strings. So when you go to actually prove that the resulting construction is post-quantum secure, you kind of need to enforce that using the cryptography. So kind of in the real world, you can imagine that the prover actually does have like a superposition of oracles, and you need to force him to, you need to kind of force him to not use that power using cryptography. All right, so let me just talk a little bit about some of the constructions. So I mentioned one in the previous slide, but this kind of is a more general overview. So all of these constructions basically follow the same kind of 3-step paradigm. So you have some idealized proof system, you compile it, and then you get a post-quantum SNARK. So the first one is Aurora. This is a construction from I guess a couple of years ago now. And this is a zero knowledge IOP for all circuits, which has linear time verification. So this is like this not sublinear verification, but you do get zero knowledge. You apply the cryptographic compiler, this BCS compiler, and you obtain a SNARK with the sort of same properties. So we follow this up with an IOP for structured circuits, which has super fast verification. So like sort of polylog verification. You can apply, again, the same cryptographic compiler, and you get a SNARK for structured circuits with, again, the super fast verification. So here the structure is kind of necessary because you need to be able to describe the circuit in a succinct way. Otherwise, the verifier needs to read some description of the circuit, and if the circuit is unstructured, then this is going to be a linear size description. Now we move to a slightly different setting. So this is sort of our most recent construction. It's a sort of pre-processing IOP for all circuits with super fast verification. So essentially, you get around this restriction of the verifier needing to read the entire circuit by pre-processing the circuit in a way that is sort of independent of the input to the circuit. So it just depends on the kind of layout of the circuit itself. And then you can like use this preprocessing step many times to prove a bunch of different statements about the same circuit. When you compile this this object using a slightly different cryptographic compiler, what you get out is a preprocessing snark. Again, for all circuits with this sublinear verification. So essentially the same properties, but now in the snark setting. In addition, there are other works which sort of use the cryptographic compiler that that we developed. So there's this like BBHR IOP for machines, and if you compile it, you get a snark for machines. I should also say that a lot of this stuff has been used by some sort of blockchain companies, so like cryptocurrency companies. Okay. In addition to all of this kind of theory stuff, we also have done some implementation work. So I'll go through this pretty quickly. Basically, Aurora and Fractal are both implemented, and the structure of the implementations is very similar to the kind of structure of the kind of theoretical constructions. So you have like some IOP that you start with, you apply a cryptographic compiler, and you obtain a snark, also in code. One thing that's nice about these proof systems is that because you are basically like you are looking at information theoretic security in the random oracle model, you can make some like estimate about the security parameter. Like you can make some sort of concrete estimate about the security parameter, which allows you to kind of set parameters in the real world. We also implement some useful so other protocols like the Fry low degree test. This gives you basically the most comprehensive library out there for building post-quantum snarks. Okay, so I guess I have about 10 minutes or so, maybe 15. So I want to talk a little bit more about the techniques, so the sort of stuff that underlies these constructions. So before I go there, I want to kind of go back to like this line of work on efficient PCPs. And actually, we're not going to talk about efficient PCPs because there actually is not that much work on efficient PCPs. Instead, we're going to talk about short PCPs, because if your PCP is long, then certainly you can't write it down in time which is like less than the length of the PCP. So the proof length is a lower bound on the proving time. Okay, so what is this kind of seminal result about PCPs tell us about the length of a PCP? Basically, for every epsilon greater than 0, if you have a time t computation, you can prove it using a PCP of length t to the 1 plus epsilon, and verify it in time, so log t to the order 1 of epsilon. So clearly, as epsilon goes to 0, the proof length goes to order of t, which is optimal, but the verified complexity will, go to infinity. So you can't really you can't bring this all the way down to order of t. And so this kind of has resulted in a lot of work on short PCPs. So there are kind of bivariate PCPs, univariate PCPs is like categories of PCPs that are shorter than this. After all of this work, you basically end up with proof length, which is like t times polylog t, and verified complexity, which is polylog t. So this is kind of, this is circumvented this trade-off. The problem is here that c is fairly large. I think it is not an explicit constant in these works, but it's sort of we expect it to be reasonably big, maybe 10. More importantly, these are the works that kind of give you this these PCPs that have these parameters. So they're kind of you're not quite there. So then, I was talking about interaction earlier in this talk. How can interaction help us with this proof length problem? To understand that, we have to look a little bit closer inside like what makes up a PCP. So I'm going to talk a little bit about codes. So I assume most of you know what a code is. If not, just think about like a bunch of strings where if I have two strings that are different, then they're very different. That's the basic definition of a code. And a PCP, like the Bentazon Sudan PCP, can be broken down into a number of parts. So to start with, you have an arithmetization. So this is like you take a computation of some kind and you convert it into a problem about code words. Then you have a proximity test. So this says, you give me a code word that is corrupted in some way, and or rather, I give you a word, and I want you to tell me whether it's close or far from a code word. Then there is some kind of property testing, like you want to check, like I give you a code word and I want you to check whether it belongs to some like subcode of the code that has a certain property. And finally, there is a component called proof composition, which I will talk about in more detail in a little bit. The basic message is that interaction can actually make every part of this PCP more efficient. So there's like interactive arithmetization, there are interactive proximity tests, interactive property checking protocols, and interactive proof composition, and all of them are sort of more efficient than their non-interactive counterparts. So this can really, really help. And moreover, it turns out that in the sort of relevant places, you can also use interaction to obtain zero knowledge in an efficient way. So the interaction allows you to basically like add zero knowledge to all of these 2, 3, and 4. So I'm gonna kind of skip over these other 1, 2, and 3, but I want to talk a bit more about proof composition because I think it demonstrates kind of ways in which interaction can help dramatically. So what is proof composition? So let's say that I have some PCP pi1. And I have my verifier, this vPCP1, that is making some queries to pi1. And my goal is to reduce the complexity of the verifier. So what I do is, rather than just running the verifier, I attach another, like I send you another PCP. I produce another PCP. And the PCP basically says the verifier accepts when querying pi1. And then I have a new PCP verifier that basically makes queries to pi2, and then makes like 1 or 2 queries to pi1 to check consistency with what pi2 is saying. And if your PCPs have certain properties, then this like vPCP2 will be much more efficient than vPCP1. So what is the cost here? The cost basically is in providing these proofs pi2. So this R here is like the randomness of the PCP verifier, the PCP verifier 1. And so I need a proof pi2 for every choice of this randomness. Like I need to supply a proof for every choice of this randomness. And so the number of these proofs is like 2 to the capital R. And so the number of the total proof length is sort of pi1 plus 2 to the capital R times pi2. Which if you sort of do a computation is roughly the product of the length of pi1 and the length of pi2. So this is like standard PCP proof composition. What is interactive proof composition? So it's actually it's a fairly simple concept. So now I have an interactive protocol. And rather than writing down all of these subproofs, all of these little pi2s, I just get the verifier to tell me which of the randomnesses he's interested in, and then the prover just sends over that kind of pi2 for that particular randomness. So you can prove that this is sound. This is a sound composition, And the proof length is pi1 plus pi2, because I didn't have to write down proof for every sort of choice of the random string. So this is, in general, going to be much smaller than the product of the two things. And more importantly, if you compose sort of more deeply, so if I do like k levels of composition, then what I pay in the interactive setting is just the sum of the proof lengths for kind of each of the subproofs. So this is like I compose once, and then I compose that proof with something else, and so on. So in the interactive setting, you're gonna pay in the sum of the proof length, whereas in the non-interactive setting, you pay in the product of the proof lengths, which is potentially kind of exponentially worse. Okay. Finally, there is you can also talk about zero knowledge, and in the interactive setting, zero knowledge for proof composition is quite relatively straightforward to achieve. So here you need to make an additional assumption, which is that the set of accepting instances along with their proofs is an F-linear space. So for some finite field F, that is like if you have a proof which is accepted by the verifier on X, and another proof which is accepted by the verifier on X prime, then if I take kind of the linear combination of the proofs, then the verifier will accept on the same linear combination of the X and X prime. So how does this help us achieve zero knowledge? So let's imagine that somehow I've made like this pi1 zero knowledge, and I just want to make sure that by doing proof composition, I don't leak anything else. So what I do is I provide you, in addition to pi1, I provide you with a uniformly random instance and instance proof pair. The verifier is now going to choose a random alpha in the field and a randomness for the kind of inner the v2 verifier. And the prover is then going to send a proof, which is the sorry, this is the v1 verifier. The prover is going to send a proof pi2 that the v1 verifier accepts the linear combination of these two proofs, pi1 and pi1 prime, on input like alpha x plus x prime. So this will, because of the linearity property, this will be a correct proof. And the important thing here is that this is a random instance and a random proof, because I basically kind of, because I added a random instance and a random proof, and this is an F-linear space, then I will end up with a random instance and a random proof. Okay. And the proof length here is short still. So it's like twice the original like pi1 proof length plus a pi2. So the message is basically that in the interactive setting, proof composition is a sort of more flexible tool. Like it's something that you can apply also for practical purposes. So you have like smaller overhead, larger possible recursion depth, and efficient zero knowledge. Okay, so I guess I have 2 minutes. All right, so I will like kind of breeze through this future work stuff. So one of the kind of main questions that we'd like to answer is, okay, so we have these post-quantum stacks from IOPs, and they have these like pretty nice efficiency properties. But if you're willing to kind of throw away the requirement that you're secure against quantum attacks, then you can basically be a lot more efficient in every respect by using kind of pre-quantum cryptography. And the kind of most important difference is that the proof size, or the argument size, is 1,000 times smaller for the best kind of pre-quantum system versus the best post-quantum system. And this, in many situations, makes a huge difference. So, we're looking into this, like trying to close this gap, and we've made quite a bit of progress already. But there are some new ideas required, I think, to really close this gap significantly. Some of them include lattice-based vector commitments and applying recursive proof composition. I'm also interested in kind of the more theoretical foundations of proofs. So, you know, we prove security in the random oracle or quantum random oracle model. Can you prove security from standard assumptions? This is kind of the big question in the study of snarks. This is a really hard problem and requires some sort of new ideas to circumvent this impossibility. Another question is, how do security reductions change in the quantum setting? So we've seen this already with the quantum random oracle, but there are also, you know, problems with things like quantum rewinding, which you know, present some challenges. And finally, what are the limitations of post-quantum proofs? Like, is there a sense in which this gap, this like gigantic gap in proof size is inherent if you want post-quantum security in some model? Finally, there are also some interesting questions about the complexity theory of IOPs just sort of by themselves. So one of them is, can you build linear time provers? So we know sort of quasi-linear time provers for IOPs. This might require sort of designing new codes or combining codes in interesting ways. And finally, the IOP sliding scale conjecture. So this is like the interactive version of the PCP sliding scale conjecture. It could be easier. All right. So with that, I'd like to say thank you very much for attending my talk. I also like to say thank you to Alessandro, who has been an excellent advisor, continues to be an excellent advisor. And without his guidance, none of this stuff would have happened. So, you know, thank you very much. I'd also like to say thank you to my esteemed co-authors. This is just a selection of them. I guess some of them probably are here. So Tom Gurr, Elie Ben-Sasson, Dave Oja, Pratyush Mishra, Benedict Buntz, and Peter Manaha. All fantastic people to work with, and I hope to continue working with you in the future. And then, of course, you know, the other Berkeley and otherwise graduate students. You know, this department is this group is really an excellent place to work, primarily because of the other students in it. And you guys have made it a really fantastic experience. So thank you very much.
Are there any questions for Nick?
So I have a quick question. Thanks for the great talk, by the way. So there was some work by Bonnet et al., I think, in constructing these. They didn't get it from LWE, but some assumptions that they conjectured were, you know, LWE-like, so perhaps had post-quantum security. I guess they're not efficient, but maybe you cited it and I missed it. How efficient is that construction? How does that compare?
So concretely, I think we don't know. So there is one thing that sort of excludes that construction, which is that it's only privately verifiable, or like designated verifier, which means that it's sort of less useful for a lot of these applications. But this is definitely, I mean, this is a very interesting direction in building more efficient snarks. I think the asymptotic efficiency is actually extremely good. It's like order of lambda, like something like that, linear in the security parameter, I think. But it is designated verified.
Okay, thanks.
No. Any more questions?
I have a question. So you need the random oracle model for probably doing Fiat-Shamir. So what else do you need it for? Have you tried using this correlation interactability to remove the random oracle assumption?
So that is like a very natural suggestion. And I would hope that something like this will eventually work for protocols like this. So the only, really the only reason you need the random oracle is for doing Fiat-Shamir type stuff. I mean, so in the construction that I was talking about, you also use it as your collision resistant hash function. this allows you to basically, give this like information theoretic guarantee in the random oracle model. But you can kind of use a standard CRHF, and then the question is like, what do you use to do Fiat-Shamir? And maybe there is some answer in terms of like correlation interactability. The only thing that I would be concerned about is that this like I don't see how this sidesteps the Gentry-Wicks result. So maybe there is something.
Those are actually non-black box, right? You make non-black box use of cryptography in this correlation interactability.
So I guess let's see. So I mean, if I were to wait, okay. So I guess correlation interactability by itself is not a falsifiable assumption, so it would be okay. So there would be, and the way that you build them is in some cases non-black box. So maybe it would be all right. There is a certain kind of so Gentry-Wicks applies to a certain kind of non-black boxness, which it's like a weak sort of it applies to a weak kind of black box use of cryptography, but it might be, yeah. I mean, this is definitely worth exploring. I can't say sort of directly, but I think that this is like one of the most promising avenues for getting this. Any more questions?
Well, if not, thank you, Nick, for the fantastic work in these years. It was certainly a lot of fun to work with you and also many other colleagues. So congratulations on this milestone.
Thank you.
A big congrats.
Okay.